Catalytic reforming represents a chemical procedure employed in transforming low-octane petroleum refinery naphthas derived from crude oil into high-octane liquid products termed reformates. These reformates are esteemed blending components for high-octane gasoline. The method involves converting low-octane linear hydrocarbons, paraffins, into branched alkanes, isoparaffins, and cyclic naphthenes, followed by partial dehydrogenation to yield high-octane aromatic hydrocarbons. Naphtha, a complex mixture of various hydrocarbon compounds, exhibits an initial boiling point of approximately 35 degrees Celsius and a final boiling point of around 200 degrees Celsius. It encompasses paraffin, naphthene, cyclic paraffins, and aromatic hydrocarbons spanning from those containing 6 carbon atoms to those with about 10 or 11 carbon atoms. Principal reactions in catalytic reforming encompass dehydrocyclization, isomerization, and dehydrogenation. Undesirable reactions such as dealkylation and hydrocracking occur due to the diminished value of resultant light hydrocarbon products. Catalysts frequently feature platinum or palladium, or a combination of a group 8 metal and a secondary catalytic metal serving as a promoter. Examples of promoter metals include rhenium, tin, tungsten, germanium, cobalt, nickel, rhodium, ruthenium, and iridium. Hydrogen, a notable byproduct, is extracted from the reformate for recycling and utilization in other processes. A catalytic reformer comprises a reactor segment and a product recovery segment. A feed preparation segment incorporates a blend of hydrotreatment and distillation, facilitating the preparation of the feedstock to desired specification. In a petroleum refinery, platforming reactors are vessels specifically designed and utilized within the platforming unit for catalytic reforming processes. These reactors facilitate the conversion of low-octane petroleum naphthas into high-octane liquid products known as reformates. Platforming reactors provide the controlled environment necessary for catalytic reactions to occur, including the conversion of low-octane linear hydrocarbons into higher-octane branched alkanes and cyclic naphthenes, followed by partial dehydrogenation to produce high-octane aromatic hydrocarbons. Additionally, platforming reactors play a role in temperature and pressure control, hydrogen separation, and product recovery within the platforming unit. They are essential components in the production of reformates, which serve as premium blending stocks for high-octane gasoline. Catalytic reforming reactors are thick-wall pressure vessels found in the petroleum refining industry. The reactors are commonly fabricated from C1/2 Mo, 1 Cr 1/2 Mo, low alloy steels and may require a wall thickness up to 4 inches to withstand inmol pressures of 400 to 600 psi at temperatures in the creep range. Within a catalytic reforming reactor, gas streams comprised of 50 to 80% hydrogen and other hydrocarbons are reacted in the presence of a catalyst at temperatures between 900 degrees Fahrenheit to 1050 degrees Fahrenheit to produce a reformate of higher octane. The reformate can be blended with other refinery product streams to increase the value of the product. Typical damage mechanisms for catalytic reformer reactors include creep, thermal fatigue, creep-fatigue interactions, brittle failure, hydrogen embrittlement, temper embrittlement, and high-temperature hydrogen attack, HTHA, leading to decarbonization, hydrogen voiding, methane blistering, and micro-fissuring and cracking. Creep, stress rupture. Occurs at high temperatures due to deformation of stressed components under loads below yield stress. Deformation leads to damage that may eventually lead to a rupture. Creep damage is not reversible. High-temperature hydrogen attack. Hydrogen decomposes into atomic hydrogen at the surface and enters the steel. At the elevated temperatures, this hydrogen reacts with carbon, from carbides, to form methane, CH4, at grain boundaries. The resulting decarbonization lowers material strength. Methane pressure builds up, forming bubbles or cavities, and microfissures at grain boundaries. Eventually, fissures may combine to form cracks. Blistering at internal locations may also occur at an advanced stage. Failure can occur when the cracks reduce the load-carrying ability of the pressure-containing part. Oxidation. Oxygen reacts with carbon steel and other alloys at high temperature, converting the metal to oxide scale. It is most often present as oxygen in the surrounding air. Approximately 20%, used for combustion in fired heaters and boilers. Oxidation of carbon steel begins to become significant above about 1000 F, 540 C. 1.25 Cr 0.5 mO at 1100 F, 595 C, and 2.25 Cr 1 mO at 120 F, 650 C. The 300 series SS are resistant to scaling up to about 1500 F, 815 C. Thermal fatigue arises from cyclic stresses induced by temperature fluctuations. It manifests as cracking within metallic components, particularly in areas where relative movement or uneven expansion is restricted during repeated thermal cycling. Carbonization. Carbonization involves the absorption of carbon into a material at high temperatures, typically in contact with a carbon-rich environment. This process renders steel brittle and susceptible to spalling or cracking. Carbonization can also diminish the remaining thickness of sound metal walls and may compromise the corrosion resistance of stainless steel. Metal dusting. It is a form of carbonization resulting in accelerated localized pitting which occurs in carburizing gases and/or process streams containing carbon and hydrogen. Pits usually form on the surface and may contain soot or graphite dust. Metal dusting involves a complex series of reactions involving a reducing gas such as hydrogen, methane, propane or company. It usually occurs in the operating temperature range of 900 degrees Fahrenheit to 1500 degrees Fahrenheit, 482 degrees Celsius to 816 degrees Celsius. By proactively addressing corrosion issues, refineries can safeguard their assets, optimize production processes, and uphold environmental and safety standards. Investing in corrosion management not only protects infrastructure but also ensures the continued reliability and profitability of refinery operations in the long term. Thank you very much for watching the video. You may consider to subscribe, like, sharing or pressing bell icon for this video, if it is worth doing. Explore our YouTube channel, PetroCelt, for captivating videos covering science, engineering, technology, and energy topics. The primary aim of launching this YouTube channel is to facilitate the exchange and dissemination of knowledge and experiences among professionals and amateur